So yeah, welcome everyone. Glad that you made it here. I mean, it's more people than I expected, really. And I hope you are all new to scikit-learn. Will make it more interesting, I hope. No, it's an introductory tutorial, and I will tell you today a little bit about scikit-learn. Give you some examples for how you do predictive modeling, and I think not everyone has a notebook or laptop with them, or her. And I have a Jupyter notebook. You don't have to really execute it in parallel while I'm talking. We will walk through it together, and we will just see how it goes. And just to quickly introduce myself, my name is Sebastian. I'm originally from Germany, but yesterday I just came from Michigan, which was almost convenient. I've been at Michigan State for almost 5 years now, I would say. And was a 3 or 4 hour drive, but I'm happy that I made it here yesterday night at some point. Okay, so then let's start. So just a few infos here. So I have the GitHub material, the material on GitHub if you want to check it out later on, maybe as a reference or something like that. And if you'd like to contact me, my email address, website, Twitter, GitHub account, and what have you. And I think because it's an introductory tutorial, I thought it would be cool if we can maybe ask a few questions and have a little bit of a back and forth. Maybe not too much, but I think because, I don't want to give a lecture here, it's really more like a tutorial, I hope. So if you have questions, then please raise your hand, and we will maybe hopefully discuss this a little bit. And I'm not sure how many of you have used machine learning or scikit-learn yet. Oh, too many. So I hope it will not be too introductory, but for the ones who didn't raise their hands, what can machine learning do for us? So I plan to insert many more pictures here, but it's always a little bit tricky with the copyright and public domain stuff. So what can machine learning do for us? Machine learning, I think, is everywhere nowadays. We have it, I think it started maybe with a spam filter in our email clients, and we have Netflix where we can search for movies. It learns by our tastes what movies we like, makes hopefully good predictions or recommendations. Then the automated ATMs where you have some sort of text recognition or image recognition. And also now the self-driving cars. I found this little older cute one from Google where, hopefully it's maybe the pinnacle of the technology right now in machine learning that we have self-driving cars, which are more or less, hopefully reliable. We will see in a few years how that will play out. And so that is basically these are just a few examples what machine learning can be used for. But what is machine learning really? And machine learning is just automating tasks that we usually did by hand. For example, we had a programmer, she looked at a lot of data, came up with some rules, and implemented these rules. For example, in email spam classification, a person looked at what are words that are commonly in spam occurring in spam email, what words are occurring not in spam email usually, and then he derived rules and experimented with it and things like that. And nowadays, we have powerful learning algorithms, so we just give our algorithm a set of labeled data. We give it maybe 10,000 or 100,000 emails that are spam emails and maybe 1 million non-spam emails, and then it will automatically learn rules to classify them. And there are 3 big types of machine learning. We have supervised, unsupervised, and reinforcement learning. And supervised learning is just, for example, this email example. We have labeled data. We know the output already. So we have emails. We know that it's a spam email or not. And in unsupervised learning, we want to discover a pattern. For example, clustering analysis. We don't know anything about our data, but we want to find a hidden structure in that. And also, maybe we want to compress our data. If we see some structures in it, we can maybe break it down into a smaller dimensional subspace to maybe increase the learning speed or accuracy, also the storage space. And reinforcement learning would be, for example, the self-driving car, a chess computer, or maybe the Go engine that was pretty popular in the last couple of months. It's basically learning by doing, so there's a reward in the environment, and the system learns incrementally by taking actions and then getting a certain reward over a certain number of steps. I think today we will focus more on supervised learning because we only have 120 minutes, I think. So we will have a reasonable coverage of at least one of these areas. We will talk about mostly supervised learning. And when we break down supervised learning, we can basically say the big categories are regression analysis and classification. In regression analysis, we have a continuous output variable. So we have a continuous input or a binary input, and then we want to predict a continuous output variable. And in classification, we have hard labels. You can think of it as categorical labels that are nominal. There's no order in the labels. We have, for example, class 1, class 2, class 3. But unless it's a ranking algorithm, there is no, can't say class 2 is greater than 1. It's basically like categories. You can also think of it as names or something like that. And in unsupervised learning, like I said before, we have clustering analysis and compression dimensionality reduction. And in clustering, we want to find groups of similar items or similar samples. And in compression, we want to find a structure so that we can break it down into smaller parts or smaller subspaces. In this example, I just took this on the lower right. It's an example of a concentric circle data set. That's a synthetic data set. And here I used a dimensionality reduction algorithm. I think I used kernel PCA to reduce it onto a one-dimensional substrate. I mean, I didn't label the y-axis here to indicate that it's just one dimension here. And as you can see, it nicely separates similar atoms from each other so that we could use a linear classifier to separate, let's say, blue from red. And we will look into this in more detail later. And I think we should maybe start with a linear regression example, a simple linear regression, because it's maybe the simplest introduction, I would say, the smoothest introduction. So you probably, all of you used a linear regression. So what it is all about, we want to model the relationship between two variables. We have an explanatory variable and a dependent variable. And what we basically, or a response variable, and what we basically want to do is we want to find a linear fit that can capture basically maybe a trend in the data, so that we have an x variable, an input variable, and we want to predict the output variable, and we want to learn basically this dotted line there. We want to derive this from the data, and how we do this is by minimizing the vertical offset. So we want to find the line that minimizes the distance from the line to the points, the vertical distance. And there are different approaches to this. So in statistics, we can use there's a closed form solution where you have a matrix inversion. But in machine learning, usually you use some optimization algorithm. It's more meant for working with big data sets where you maybe can't really invert a matrix because it's computationally too expensive for memory or not feasible. And so that is basically just a simple example of what we can do with machine learning. And how we represent our data also in scikit-learn later, which will be relevant, is that we have usually an X array. We use usually NumPy arrays because we can store, NumPy array stores items in a contiguous memory, which is more efficient. We can make use of our memories, the caches, the L1 and L2 cache. And it's just faster to buffer it. And if you have a contiguous memory, rather than accessing items in the list randomly, like in a Python list. I mean, the memory access is random. So, and we have a lot of powerful linear algebra functions implemented in scikit-learn or in NumPy, which also makes use of the BLAS unit of our computer, makes everything a little bit more efficient. That's maybe why we use mostly NumPy for linear algebra and machine learning, rather than Python objects like lists. And in the data representation, when we have our X array, that is basically our data, we have multiple samples, and we represent them as rows, and our features are the columns in this data array. So it's usually a two-dimensional array. And we also have in supervised learning a Y array. In the Y array, we store the class labels of, in the regression example, we store the continuous target variable. And each, for example, each index here, 0, 1, 2, 3, they correspond to the samples in the X array. So 0, 1, 2, and 3. And the columns, again, are the different features. For example, later we will also work with the iris data flower set, where we have different flower measurements, for example, petal width, petal length, and these would be features. And so the basic workflow of machine learning, how we do supervised learning, it's a little bit small here. So we, at point one, I just indicated, so we have a data set with samples and labels here on the left. And what we want to do is we want to split our data set first. Usually we want to do a random subsampling or resampling here. So we split our data set into two parts, a training set and the test data set. Usually it's maybe 2 to 3 split, like, or 70% training data, 30% test data. But it really depends on how big our data set is. And the test data, that is the important part, that we don't touch it during training. This is just for evaluating the model later on. So we don't want to have our algorithm look at this data, because then it will become biased and overly optimistic if it already has seen this. So we want to keep it secret from our algorithm. It's just for the evaluation. And in the second step, so we take the training data, we use a machine learning algorithm and learn a model, a predictive model, for instance. And I indicated here hyperparameter values, and we will talk about that later. Hyperparameters are parameters of the algorithm. For example, the number of iterations our algorithm goes through the data, and later on we will also see, for example, I'm not sure what I included it, but let's say regularization to introduce a bias by us to prevent overfitting. But hyperparameter values are basically the values of our algorithm and not the model parameters. Model parameters would be weight coefficients or the intercept. These would be model parameters. For example, here on the y-axis, this intercept term, that would be a model parameter that we learn from the data. And also how steep the curve is. That's the coefficient or weight parameter. This is something the learning algorithm learns from the data. And hyperparameters is something that we as a programmer or data scientist have to set manually. And we will also see later that there are different methods that we can do, for example, a grid search and automate this looking for these for good values, but it's not learned by the algorithm itself. So in the third step here, we basically use our test data then. So we have fitted a model in step 2, and we take our model, in green we have the test data, and we make predictions on the test data without knowing the labels yet, or the algorithm doesn't know the labels, so we predict the labels. And then we compare these labels to each other and see how it performs. So we compare the labels to the true labels, the predicted labels to the ones that we withheld before. And then we can compare how many mistakes did the model make. And based on that, we can compute a certain performance. There are different performance metrics. We will talk about this later, I think. And in step 4, after we evaluated our model, there's actually no good reason why we should not also show the test data to the algorithm, because the test data, the purpose is to really compute the performance or estimate how well it would do in the future on unknown new data that has been sampled from the same probability distribution as our training data. But once our algorithm, or once we evaluated our algorithm, there's no point in withholding it, because usually the more data the algorithm has, the better it performs. We will later also look at learning curves, which is an indicator that algorithm may benefit or not benefit from additional data. So now we can, in step 4, after evaluation, we can take our whole data set and use the same learning algorithm that we evaluated before and learn the final model. So we use the same settings as before, but here we use more data, which is usually resulting in a more robust model. And then, yeah, one question? Yeah, we will talk about that later. So the question was if we do this basically in one step, or if there are multiple iterations that we learn different models and evaluate different models. Yeah, that's a good point, and we will get to this or later when we look at how we can optimize our hyperparameter settings. But if we only have a training and test split, I wouldn't recommend this because you can easily do an overfitting if you would reuse your training set. or for example, if you would change the hyperparameter in step 2 and evaluate the performance again, and then you would change it again and evaluate the performance again, then you would basically incorporate your test data in a training procedure. So you would optimize your model also kind of towards making good predictions on test data. And this is kind of cheating, I would say. So your estimate here, it would not be that unbiased anymore. So you would introduce some bias. It would look better than it really is, basically. But we will talk about alternatives later. So this is basically the simplest workflow. When you already, for example, in scikit-learn, use the default parameters, and you just know what algorithm you want to use. You don't want to compare algorithms. It's the simplest workflow where you provide a known algorithm, a hyperparameter value setting, and just evaluate the model. And yeah, I've prepared some code examples because it's I hope a scikit-learn tutorial. Not only just about machine learning concepts. So I hope it is, I can make it bigger, I think. So hopefully it works here. So we'll also use matplotlib and pandas a little bit, as they are convenient libraries that can help us with visualizing our results. And pandas, I like it a lot for working with or pre-processing data. If you collect data from different sources and you want to combine columns or merge data sets, or cleaning up a data set, find pandas very convenient for that. But for the main machine learning data input for scikit-learn, we usually use NumPy. So first, we will work with a linear regression example, and I don't know. I didn't want to use the Boston dataset again. I think it's a very popular dataset, but it's kind of boring already. So I just did a search online what kind of datasets are available for a simple regression example. I found this dataset that compares the relation of the brain, the size of the brain, to the size of the head. So is there a relationship between head size and brain size, which is kind of interesting. So how this data set looks like is we have two classes. No, it's a regression example, sorry. So let me see how it looks like. So these are the last 5 rows of the data set. We have 237 samples, 36, I think. And we have the head size, it's a continuous variable, and in cubic centimeters. And we have the brain weight in grams, which is also a continuous variable. And we want to use, for example, can we use the head size to predict the brain weight? Would be, for example, one question we could ask. Could we build a model that can predict the brain weight based on the head size? And how this data set looks like, if we just put a scatter plot, I think, a question? Oh, yeah, sure. All right. So I always find it helpful to first visualize a data set. To just it's not always so easy because usually we are working with high-dimensional data sets. But if we have a 2D data set or maybe a 3D data set, we can easily do a scatter plot. And if it's more than 3D, we can maybe do multiple histograms to just get a quick idea of how the data set looks like. If it even makes sense to build a model on that. If, for example, the data is completely random, we don't see any correlation, I mean, that's probably not a good idea to build a model because it probably won't work. We can still try, but it gives us at least some idea what we are working with. And in this case, it looks like this. So we have on the x-axis the exploratory variable, the head size in cubic centimeters, and the brain weight is what we want to predict in grams. And this is our data set that we will use to build a simple linear regression model. And I don't know, but I think there's a pretty nice correlation here. I haven't quantified it here in terms of R or R squared, but it looks to me very correlated, or not correlated. And to prepare the data set, so usually I said we are using NumPy for scikit-learn. We use maybe pandas because it's convenient to read a CSV file in here, or here in this case it's a text file, where the columns are separated by a certain number of white spaces. But I think it is yeah, so more convenient to use pandas for that. NumPy's CSV reader can be sometimes a little bit tricky. But for scikit-learn, we want to convert it now into NumPy array. So via the values attribute of pandas, we can access NumPy, an underlying NumPy array. You can think of pandas be built on top of NumPy with a few, top of pandas with a few extra convenience functions. So first we will access the 237 class label continuous outputs. This is now a NumPy array. Can maybe and then we do the same thing for the head size. And one important thing when we work with scikit-learn, so when we just convert or get the NumPy array from our head size column, it will be a one-dimensional array. So there's only a number of rows. We don't have a second axis here. And for scikit-learn, it's important. A lot of bugs arise if we don't pay attention to this. So NumPy expects a two-dimensional array. So we have to, in this case, because we only have one column, we have to use, for example, we can use none here or NumPy new axis to add a second axis to our NumPy array, so that we have the 237 rows and one column, so that it's a NumPy array of two axes. That's important for compatibility with scikit-learn. So just take this chance. So any questions so far? Yeah? I think mostly it's gotten better, so I think it works oftentimes also with pandas, but I think it's not, I think, officially supported, so there may be some problems or bugs that could come up with using pandas. Usually it works, but I think it's not much hassle to just use this values attribute to get the NumPy array. I would recommend it. It's not always necessary, but you can get, I think I've seen some cases where it led to bugs when you use the pandas array directly. In NumPy, you mean? So you mean, for example, the X array only has the columns, but not the names of the columns, so only the index. So usually, you have to maybe you can make a dictionary maybe if you want to know the names later, but you have, for example, the columns attribute, and if you use all of the columns, you could also just use the index. For example, in this case, you can use the brainweight, the index later on. Usually, you just keep track of it when you do the conversion. You have a table, and we can later maybe make do an example where we compute feature importance and then map it back to the actual labels, where we only have indices, and then we can maybe get the labels back from the pandas array. We can at the end maybe make an example that would be a nice one. Okay, so now we have our NumPy arrays, continuous variable in y that we want to predict, and one continuous variable in the X array, one column. And yeah, in the first step, we want to split our data set into two sub data sets, a training data set and a test data set. So there's a convenient function, the train test split function in scikit-learn. And here we can either set the train size attribute parameter 2.3, which will then put 70% of the data into the X train data set and 30% of the data into the training data set. And here I use the random state. I think for like scientific experiments, it's a thing recommended so you can reproduce your results. So if I do the split, it will always result in the same split if I use the same random state. And maybe I can just show you. It's a smaller array now. Oh, sorry. We have 237 samples to start with. After the splitting, we have 70%, 165 samples. And how this looks like is like this. We have the blue ones are the training samples, and the red ones are the test samples, the squares. And what I wanted to show you, I think, here is that it's a random split. So what happens, it's also shuffling it, which is also important, that we, for example, not only take this lower part as training set and the upper part as test set. So it does the shuffling for us already. Yeah, and then we can fit a model. So in the linear model submodule of scikit-learn, we have several linear models for classification and linear regression. We'll only use the simple linear regression one without any regularization. And how this works is we initialize object, linear regression model that we, or object that we will fit to get our predictive model. And in supervised estimators, like linear regression, we provide both the X train or and Y train, the labels and the variables. And then we can make a prediction via the predict method. And that's the basic workflow for classification and regression in scikit-learn. It's a very nice API. You have a fit method to learn the model parameters, and then you use these model parameters to make predictions on the test set. And yeah. So we will, I think, look at it in a second, but or you can maybe you can do it like this. Sorry, the question was if we call the fit method, will it modify our LR model? So that was the question, right? So yeah, so this is basically here a blank blank object with certain attributes that are not assigned yet. And if we call fit, it will get certain attributes like the intercept term or coefficient. So for example, it should have, I think, this one, no? This is our slope of the linear regression model. And in scikit-learn, by this underscore, the trailing underscore, it basically indicates these are attributes that are available after model fitting. I think so. For example, if I would do it like this, there won't be any coefficient attribute, I think. Yeah. So has no object coefficient. So this will only become available after fitting. Yeah, and to evaluate our model here, how well does it fit our data? Scikit-learn for classifiers and regression estimators, they have a score function. And for classifiers, we'll see later the score the score method is using accuracy as a metric. And for regression models, it will use the determinant of coefficient of the coefficient of determination, so the R square score. And here I just computed it manually just to check that we get the sum results as a illustration. So the linear regression estimators, all of them in scikit-learn, when you call score, it will compute the R2 score, which is here computed based on the X test and Y test label, the Y test labels. It tells us there's pretty decent variance explained by the model. It's of course not perfect. The score ranges from 0 to 1, but I would say it's pretty okay. Depends on your expectation, of course, but yeah. And here what I showed above, the two terms that are now available, the slope of the regression line and the y-axis intercept. And here just to illustrate how our linear regression fit looks like. So I just took the So this is, 1 second. So the prediction is basically done by, let's say, where C is our y-axis intercept, and let's say A is our input data, and B is our coefficient. And by this equation, we can compute or make a prediction on new samples. And here I just use the min value of our training set or max value to draw a line between those 2 points to illustrate how our regression fit looks like. And yeah, of course, it's a linear regression. We have some deviations here from the linear regression line. But I think it's a pretty decent fit in this case. There may be some outliers here, this one maybe, that may drag the line in a certain way a little bit up and things like that. But overall, yeah, this is just an example of how to use scikit-learn moreover. I mean, using the fit method, the predict method, and the score method to evaluate our model. Just, yeah. So before we go to the next section, are there any questions? I thought it was an introductory tutorial, so I hope it's not too easy here. Yeah. Yeah, so I just showed you the, sorry. So the question was if I could explain a little bit more about the scoring functions available in scikit-learn. So in this case, I only showed you the default, the .score method. And in scikit-learn, we have multiple scoring metrics. Do we have Wi-Fi here, by the way? Also, 1 second, I have to plug in my. So in scikit-learn, there's a metrics module, I think, and they list several different performance metrics that you could use alternatively. When we do the hyperparameter tuning example later, I also will show you how to use this in during the model selection. I think it's this one. So you would have to, I think I don't have internet here, but I'm not sure how to get a list of all these performance metrics in the metrics module. But for example, the R-score is also available through the metrics module. So and there are other ones. For example, I think it should be a mean squared error one. No. Maybe it's spelled a little bit differently, but they have for regression also different scoring functions here in the metrics module. You can, excuse me? Yeah. Cross-validation. Yeah, we'll get to that towards the end of the section. I just want to give you a brief overview of how the estimator works in general with the fit method, the predict, and the score. And then later we will talk about cross-validation, which is, I think, very important. So then let's maybe get back to the presentation. So that was just a quick overview to show you the general API of scikit-learn. Yeah, because it's a scikit-learn tutorial, I thought I was I should focus a little bit about the API itself rather than machine learning, because we only have so many minutes. So just as a reminder, these three functions are the most essential ones in the supervised estimators. In the unsupervised methods or estimators, we will see later, it's a little bit different, but only slightly. And that's all you need to get started. But later we'll also see how we can tune these hyperparameters and set different hyperparameter values. And yeah, a classic example, I mean, it's maybe known to most of you, but I think it's still, for an introductory tutorial, a nice data set because of its properties. We can visualize this data set, and also the scaling of the variables is convenient to explain. Yeah. So we have a iris data set. It's probably most of you heard of it, but I will just still talk about it briefly. So there are 3 different flower species: Iris setosa, Iris virginica, still labeled it wrong, Iris virginica, and maybe just should be like this. Okay. So 3 different flower species, and what we want to do is we want to use the flower measurements, for example, the width and height of these leaves, to predict whether it's a setosa, versicolor, or virginica flower. And we have 150 flowers in this data set, 50 flowers from each species. And again, we represent our data set as the features as columns, the measurements of these petals and sepals, and each sample is 1 row in our data set. And in our Y-array, we have the labels. And so when we use the train test split function in the previous section about regression, we just randomly split our data set. And we can also do that here. We have 50 species from we have 50 samples from each species. But one problem is that we slightly shift the distribution of class labels. So for example, here we have a 33% proportion of each species represented in the whole data set. And if we use the train test split function, we will slightly alter this depending on our random split, but it won't be 33% anymore, which I illustrated here. So what I mean by that is we change the frequency of how often each class label occurs in the 2 subsets, test and training set. So here I used a certain random seed, doesn't matter which one, but in this case I got, for example, 38 setosa, 28 versicolor, and 34 virginica flowers. So it's not all even. It's before we had 50, 50, 50, and now we have a slightly different distribution in the training set if we just use a random seed. And the same for the test set. It will be basically changing in the opposite direction. So we will also then, in the notebook in a few minutes, see how we can stratify the split. That means that we can maintain the class proportions. And I think that's a relatively new feature in scikit-learn. I think it was added in version 70.1, I think, or 17.0. And just a quick recap about the linear regression that we just did. So what happened was we had only a simple linear regression example where we only had 1 weight and 1 intercept. So we can picture it as we had 1 input variable and then 1 intercept term and 1 weight. And we put it through a net input function. So we summed up, or we only had one. We only had 1 input that we multiplied by our weight, and got then basically if we would have multiple ones, we would get a linear combination of these. And for the classification, we use in the following example just a logistic regression classifier. The name is maybe a little bit confusing. It's called logistic regression, but it's a classifier. And how it is different from this linear regression is that we now substitute this linear input function or a linear activation function by a sigmoidal shaped one. In this case, it's a logistic function. It's 1 over 1 plus e to the minus z, which is, so the exact equation doesn't matter, but what I want to say is it's a non-linear function here. And overall, this is a generalized linear model because there's still a linear dependence between input features and weights. And at the end, so we can use this one to make a prediction about the probability. How likely is it that a sample has a certain class? But we can also add in a logistic regression classifier this unit step function, which will basically just say if our output of the sigmoid is larger than 0.5, then it will be, let's say, class 1. If it's smaller than 0.5, it will be class 0. And it's similar to the linear regression here, in that we compute the net input, but we substitute the linear function by a sigmoid function, and we add a unit step function to it. Yeah, but you could also use a linear function for this 0.5 split. If I draw it like here, if you think of the cross as an x and y and this as the intercept, you could also say if the input is greater than 0, it's class 1. If it's smaller than 0, it's class 0. And that would be an Adeline classifier, an adaptive linear neuron. It has been invented, or people came up with it in, I think, 1950s. But the logistic regression is a little bit more robust because, let's say you have outliers, you can basically show that it's a posterior probability. So with this one, it will just shoot straight up. If you minimize this, the minimization, it's a little bit trickier with outliers. You have not such a nice minimizer. It's also a convex function, but it's here directly related to probabilities, so which is a nice property of this. And yeah, but you could also use a linear function here, which would be then an adaptive linear neuron, but this is not implemented in scikit-learn. It's not used in practice anymore. It has been used, I think, after the perceptron in the 1950s. But you still use linear activation functions in certain neural networks nowadays. Okay. So that was a logistic regression. It's basically also, you can use it with, you can learn it with optimization algorithms where you optimize the weights incrementally while you go over the training set multiple times. And another classifier we will talk about is k-nearest neighbors. And this one is different from logistic regression in that in logistic regression, we give it a data set. It will iterate over the data set multiple times, and we will learn certain weight coefficients. And we just have to keep these weight coefficients. If we have new data, what we do is we put in, for example, if we have 3 dimensions, this x1, x2, and xm, we would provide these inputs. We have then 3 weights and the intercept, compute the net input, compute the sigmoid, and blah, blah. But the point is we don't have to memorize it, or we don't have to keep the data set. So we just learn our coefficients, and then we can throw our training set away, and we can make new predictions. And k-nearest neighbor is different, so it's also why it's called a lazy learner. So there's no fitting or learning step really. So all it does is at prediction time, it will look up which samples are in the neighborhood of our sample we are interested in. So for instance, if we have this point, this question mark point here, we have to keep the training set, and what k-nearest neighbor will do is it uses a distance metric to see, okay, which are the points that are closest to our point in question. And in this case, we have 5 nearest neighbors. So we are looking for the 5 closest points, and then we make just a majority vote. So in this case, I have 3 triangles, 1 square and 1 cross. So the triangle is the majority. In this case, I would then also predict this question mark as a triangle class. In this distance metric, I think the classic one is the Euclidean distance here. I think it's more the generalized form, the Minkowski distance. So if you substitute 2 here instead of the p, you will get the Euclidean distance. And here it's also important, I think, tree-based methods are the only ones that are not scale invariant. But here, also in logistic regression, depending on your optimization algorithm, and in k-nearest neighbors, depending on your distance metric, you want to make sure that your features are all on the same scale. So in Iris, it's simple. We don't have to do much because it's all in centimeters. But let's say we measured 1 in inches, or we measured 1 in miles. So the number would be much smaller, and it would appear much closer to the k-nearest neighbor Euclidean distance metric. So if we have different scales, we want to make sure it's all measured on the same scale. And we will also talk in the notebook about methods to normalize data. So let's see. Okay, I think we will go to the notebook now to look at a few examples. So again, we use pandas to read in our data set. In this case, it's a CSV file. It's labeled as txt, but it's a CSV file with comma-separated values. And this is how it looks like in pandas. And we have here, I use this text file here because we have names in the class column, which makes it more interesting. I will show you in a second how we can deal with this, because scikit-learn expects integers or as y-array variables or values. So we have 3 different class labels, 4 feature columns, and the problem now is we can't really fit it directly into, or we can't directly fit a model. Here we use a label encoder first. So we want to convert, the task is now to convert this into integers that we can use in our classifier or to fit our model. And there's one convenient class, it's called label encoder. And here we can, like in all estimators, we have a fit method. And the fit method will get the labels from unique labels from a data set and store it under the class attribute. Zeros and ones. Mm-hmm. Mm-hmm. You mean true and false? Yeah, I think maybe this would be overkill to use the label encoder. Maybe you could also use NumPy where, or you could use let's say you mean something like that, or what happens if I use okay. Yeah, something like that, but also for text variables, you could also, if there are only 2 of them, if it's like this or something, or if you have, let's say, 0.5s and some other values, 2.5s, for whatever reason as class labels, I think you can also use the something like that, right? And I don't know, I think the label encoder is more useful if you have multiple strings. If you already have numbers or only 2 of them, I would maybe use a simpler way to do it. One advantage, I think, is that you can just store this information and do an inverse. But you can also set up a dictionary. So also you could just set up a dictionary and use a map function in NumPy. So yeah, the inverse transform would be maybe handy if you do the prediction and you want to look up what variable it is. Later on, you can use the inverse transform. Maybe that is also something you could use for your columns in the pandas array that you talked about earlier, where you said, how do I know what indices refer back to the columns in the pandas array? I think that may be also one application that you can feed the columns here, and then you can get indices, and then you can inverse transform the indices back to columns and get the names. Yeah, I showed you this example to illustrate, okay, how do we convert string variables to integers, but there's also there are also a couple of inbuilt datasets in scikit-learn for testing. I mean, these are not exciting data sets, but they are data sets that are useful for, let's say, debugging or testing certain things or benchmarking. And the scikit-learn datasets module has several of these data sets. In this case, we can also load the iris dataset directly, and here it will be loaded, and then we have, you can think of it as a dictionary. So it has then certain attributes. The DESCR will give you a description of the dataset, for example. But there are several different attributes. For example, the target is our class label array. The data are our features, and we have also the target names and feature names if we are interested in these. Okay, so to make this probably a little bit more challenging for the algorithm and maybe also for visual purposes, I only choose two features for our next example. In this case, it will be the first and second one. It would be the sepal length and the sepal width. And here we have 3 class labels still and 50 samples from each flower species. 0 is setosa, 1 is versicolor, and 2 is virginica. And like I said before, maybe you want to use a stratified split. So what happens if I just split it with this train test function like we did before in the linear regression example? We get a different class distribution in the training data set, for example. The same also for the test set. So they are not 33% per class anymore. So we can use this stratify parameter and give it the Y array, and then it will stratify the split so that we maintain the distribution. In this case, we have then 35 flowers from each class. So the whole point why we want to do it is because we want to have a representative data set, assuming that our iris data set has been drawn from some real-world distribution. That in a real world, we have really 33% of each species, which may not be true, but we are assuming this when we have our training set. It's one assumption that most machine learning algorithms make. And we also want to have our test set representative of the training set. Of course, we want to learn something from a training set that also applies to new data, and we expect this new data to be similarly distributed as our model, the data our model learned from. And yeah, now we will fit logistic regression classifier. And I think in a slide, maybe it was a little bit misleading. It's a binary classifier. So I said if it's above a certain value, it will be class 1, and below a certain value, class 0. But in our iris data set, we have 3 classes, not 2. So if you use the default settings, if you would remove, for example, this part, it would use, I think it's a 1 versus 1 classifier. So it will train 3 logistic regression models, 1 for setosa versus virginica, 1 for setosa versus versicolor, and 1 for versicolor versus virginica. And then it will make the prediction based on the best score of these 3. But yeah, here I just, I don't know, I usually use the multinomial one. It's a softmax regression. It's changing the equation a little bit, so we don't have a sigmoid, but the softmax function later on attached to it, so it generalizes to multiple classes and gives us meaningful probabilities still. But it's just a side note, and we also have, yeah. I think maybe, so the question is, how did I make this choice? I think it's maybe just a personal preference, but if the classes are independent, a softmax classification algorithm should give you meaningful probabilities. I think the 1 versus 1 classifier works in all cases, but I just for theoretical reasons, I think it is reasonable to use softmax here. Yeah, it's a I think I would always maybe that was I shouldn't have done this, but I think because the scikit-learn parameters are reasonable, so there shouldn't be a reason unless there is a particular reason why you wouldn't use the default settings. They should work well. So if I just use logistic regression and look at the parameters, misspell it. So there are different parameters set by default, and I think they are usually reasonable. For example, there's a regularization parameter, but we won't go into much detail. So if you set this higher, basically you will decrease the regularization. If it's lower, you will add a bias to it. But usually you don't have to worry about it in a standard setting. This is something we do when we do hyperparameter tuning. And yeah, we have to talk maybe more about it later when we have introduced k-fold cross-validation. Sorry, I said 1 versus 1 here. It's 1 versus rest classifier. So what it will do is it will, by default, train a logistic regression classifier that learns, basically predicts the TOSA versus versicolor and Virginica, and so 1 versus 2 other classes, or 1 versus rest, basically. And we'll train 3 of these classifiers and make them the final prediction. And there are different, the solvers are just the optimization algorithms. So in this case, liblinear is efficient, I think, C++ library, which will optimize linear model or learn a linear model efficiently. I just use Newton's CG, I think, because the liblinear doesn't support multinomial, which I personally like for these cases, but yeah. I think. But anyway, so maybe we should continue. I hope, we can talk about it after the session more. I'm happy to talk more about softmax regression then. Okay, so in this case, we get a test accuracy of 80%. So that basically means it classified 80% of our flowers correctly. And we had 105 flowers, so 70% of the 150. In the test set we had fewer, we had 45 flowers. And again, like in the linear regression example, we have a fit method to learn the model coefficients. And we have the score method to make a prediction. And in a linear regression example, it was the R square. And in a classification estimator, it's the accuracy. And yeah, here I just import a function from one of my convenience libraries just to visualize how our classifier looks like. And okay. I think I have an old version installed here. So yeah, this is how our classification looks like, the results. So we have 3 decision boundaries, and red are the setosa flowers, green are the Virginica flowers, and blue are the versicolor flowers. And yeah, it makes a few mistakes. As we can see, there's overlap in, we only use sepal width and sepal length. Not sure why label is not showing. Not sure why it's not showing up here, but it should be a sepal length. And in this case, we make a few mistakes. And I circled the test samples here. And this is how our linear regression model looks like. Yeah. Mm-hmm. Yep. I have, so the question was, when someone changes the random seed, we will get really different results. And this is an effect because the data set is rather small and we have a large variance. So our estimate is sensitive to how we split our data. So there are different methods. I think I have slides about that. One would be a repeated holdout. So you would repeat this maybe 50 times, do the splitting, but each time you use a different random seed, and then you can maybe average the 50 predictions. Would be a little bit more robust. You could use bootstrapping. It's for estimating the uncertainty of your estimate. It's also resampling the data, and I think I have also slides on that. Or you could use k-fold cross-validation. Instead of a training test split, you could, if you don't tune the hyperparameters, you can also use, let's say, 10-fold cross-validation. But I have slides about that later to introduce this with a few more images to make it more clear. Yeah, and then we do the same thing with the k-nearest neighbor classifier. And as we can see, the k-nearest neighbor classifier is, we don't have linear boundaries here. And we have, for example, set one parameter here, the number of neighbors to 4. If I change it, it will also change, of course, the decision boundary. For example, if I set it to, let's say, something high, it should be smoother. And we will talk later about how to do this properly, how to choose good hyperparameter values. And yeah, and one note about tie breaking. So if I have something like, it's very rare in data sets, but if I have, for example, set it to 4 and it happens that there are two and two classes, for example, in the neighborhood, so it can't make a decision. It would just, I think, pick the first class from the data set. Or it depends on how the data set is ordered. So I usually, I don't know, but I always pick uneven numbers, so to not have any randomness in how something is picked. Yeah, if there's time, we can also go through the exercises later. But yeah, I wanted to get maybe to the model evaluation because it was a question that came up multiple times. I think that is, can maybe do the fourth section and then go to the sixth section to talk a little bit about model evaluation. Yeah, also, what do we do when we work with categorical variables? So before we had an example where we had names in the class label column, but what do we do if we have, for example, non-floats or non-integers in the feature columns? This is a very trivial example, but what I wanted to highlight here is there are two types of categorical variables. So we have ordinal and nominal variables. So the color here, the color column, if this would be a feature, this would be a categorical variable which is nominal, so there's no order implied. By that I mean, usually there are a few exceptions, but usually you can't say red is greater than blue or green is greater than red or something like that. You can't really order it. In this example, if we talk about t-shirts, for example, the size, if we order it, it may make sense. So we can say a t-shirt size XL is great or bigger than a t-shirt size L, and L is bigger than M. So we have an ordinal variable here. We can order it. And same for the price. It's already a float, but it has some weird character in front, but we also can convert it. So we have a nominal variable, a ordinal variable, and a continuous variable here. And the class labels, they look like they are also maybe if we have class labels 1, 2, and 3, they look like they are ordinal, that we can order them, but most classification algorithms, unless they are for ranking, they don't assume any order in the class labels. But the features, their algorithm would assume there's an order, so we can't use, for example, the label encoder if we have a nominal variable. If we would use the label encoder, it would maybe do something like 0, 1, and 2, and then it would imply that green is bigger than blue. But there are other ways to deal with that, and I will talk about it in 1 second. So one would be one-hot encoding. It's basically converting a nominal variable into a one-hot encoding, which means like multiple binary variables. Give me 1 second, sorry. So here we take one input variable that is nominal and split it into 3 variables. And we binarize it also. So if there is a 1 here, it means that it's a red one. So the sample is a red, this sample is blue, and this sample is 1. So we just binarize it. We make multiple variables out of 1. It's one way to deal with it, the most common way. And here we don't have to worry about one-hot encoding because we have an order. We can just use, for example, the label encoder to assign numerical values to it. But then the trick is, we as a human, we have to know which one is bigger than the other one. So I would recommend looking at the data and doing this manually with, let's say, setting up a dictionary mapping. Because how does our label encoder know that XL is bigger than L? So it's something that we as data scientists have to manually maybe verify. And then feature normalization, like I said before, most algorithms are sensitive to scale. So especially, for example, the k-nearest neighbor classifier. So there are 2 common ways to normalize features. One is min-max scaling, and one is z-score standardization. There are other methods like L2 and L1 norms, but these are maybe the most common ones. So in min-max scaling, we will let's imagine feature is our example feature, values from 1 to 6. And min-max scaling will rescale these values onto a scale from 0 to 1. And z-score standardization, in contrast, it will basically give it the properties of a standard normal distribution, that it's centered at 0. So the mean of the feature will be 0. And it will basically, you can interpret it as minus 1.46 standard deviations from the mean, these values. It's centered around the mean, which is usually the typical way to... Yeah, I think usually there's no reason why one should be preferred. There are certain exceptions. I think in people work with images, min-max scaling is more popular. But for example, for the k-nearest neighbors, I think it shouldn't make such a difference. But I think z-score standardization would be more maintaining knowledge about outliers. Here you would kind of, in min-max scaling, smoothen a little bit out the magnitude if you have extreme outliers. We don't have them here. Usually use standardization for simple optimization algorithms, such as, let's say, gradient descent, because you update the weights more equally. It's usually also in neural networks. But there are also certain ones, I think, for ReLU units, you use min-max scaling. It really depends. It's sometimes in neural networks empirical. They just try different things. Another question? No, I think there's no good reason to avoid it. Usually variables are very rarely normal distributed, but it's you just so the goal is basically just to bring them onto the same scale. So if you have completely different magnitudes, you want to have something that is centered around 0 and maybe in terms of standard deviation something from the mean. It also tells you something about your variable. And it's also useful, for example, if you standardize it and you do a linear regression with multiple weights, you can kind of see or look at the weights then. If your input variables are all on the same scale, if you have a linear model, it should tell you how important a certain feature is or how much role it plays in the final prediction. If it's a large value, the weight will be small. And if it's a, for example, for instance, so it really is only helpful usually in applications. And yeah, it has a nice property that your data is centered around the mean, which is in certain applications also for optimization algorithms a nice property. And you have positive and negative values. So you can update in both directions. Whereas in min-max scaling, you only have positive ones. Yeah, and there's also a class in scikit-learn that can do this for us, a convenience function. We can do this manually, but there's a convenience function to do this. And when we talk about this, I just want to introduce very quickly unsupervised estimators. So you can think of standardization not really as an unsupervised algorithm, but it has the same API. So you have also a fit method to deduce, in this case, if you do standardization, you would deduce the mean and the standard deviation from the data set. You will store this and use the transform method to transform any new data. And then other unsupervised estimators, they have in addition also a predict method if you use a clustering algorithm. But I think we won't go into this into more detail unless we have more time. But we'll see how we do and then maybe talk about it more later. And just to give you an idea of a typical machine learning or scikit-learn pipeline, it is also a pipeline in scikit-learn is also a convenience wrapper that allows us to put multiple estimators into one kind of workflow. You can think of it as a workflow. So we will see in the notebook in a few seconds. So we can put an estimator for scaling into this pipeline. We can use something for dimensionality reduction in this pipeline. We will talk about this maybe later. And our learning algorithm. And then we treat this pipeline as an estimator. So we also, in the pipeline itself is an object that also has a fit and transform method. So we call fit on the pipeline, and what it will do behind the scenes is we'll fit the scaling estimator, pass this data to the next part in our pipeline, pass it to the next one, and the last one, the last one should always be the learning algorithm, which basically then only has a fit method to learn the model. And then we can have it also has a predict method like an estimator, and if it sees test data and we use a predict method, it will not fit anything again, but it will use the things that we learn from the training data to pass this down the pipeline, apply these transformations, and make the final prediction. I think it will become more clear in the notebook. It's a little bit abstract here. So let us have a look at that one. So here's just, again, an example how to deal with categorical variables. It's the example I showed you on the slides. So there's a dict vectorizer, for instance, and here it takes these strings and converts it to this one-hot encoding here. And it does the same with the size, which is maybe not what we want, like we talked before, because there is an order. And also what you note here is that it will kind of shuffle the order a little bit. Because it's a dictionary, it will put, for example, this variable at the end. But that's not important. What I wanted to get at is in such cases where we know that there's an order, for example, as data scientists, we know XL is bigger than L and bigger than M. We maybe can set up a dictionary manually and use a map function to do the transformation like this, that we can convert the size to 1, 2, and 3. And then we can vice versa also do the same thing inversely later for interpretation. You want to convert it back. You can make an inverse mapping dictionary. So what I've done here is basically I did this step manually, and now everything should look fine. And if we use the dict vectorizer, it will only touch the column that is a string variable or has a string values in it, which would be color, and it will do the right thing then and do the one-hot encoding on these left 3 columns. Then briefly the normalization. Our example data set from the slides. And then we have min-max scalar and a standard scalar from scikit-learn, and it has a normal fit method here. And one convenience function, it has a fit transform method, which is just equal to if we would do this. Would be equal to this. It's just more convenient, just a shortcut for this. Okay. Now the pipelines, I think that's more interesting. That's very useful in practice. So again, we have our simple iris data set, our linear regression, logistic regression classifier. And this is just a simple pipeline because I haven't talked about dimensionality reduction yet. But here, we can use the make pipeline function to put two things into one pipeline. We have the standard scalar and we have the logistic regression. We could do this manually. We could, like before, use this output. We can get a new output here, and then, let's say, can do an X scaled, do this, and then fit our logistic regression classifier in 2 steps. But I think the advantage will become more clear why this is useful is when we do cross-validation and when we do grid search to optimize our hyperparameters, because then it will be applied to each split of the data. But you can think of it as a normal estimator that has just multiple elements inside. Yeah, one question? Yeah, so one important point, the question was, if I use the standardization, or if I use the parameters from the training data set in normalization, when I normalize the test data set. And yeah, this is a very important point. So we don't want to refit our scalar on the test data set. So if we have, let's say, a data set that has values 100, 200, and 300, and we use the standard scalar, how do I call it? I will get then, yeah, also, well, it's hard to see. Probably not enough values here, but we get the center around mean and then minus 1.2 standard deviations from the mean. So this is fine, but let's say we have a test data that is now, let's say, okay, I think just a reminder, it's not really an actual phone call, that I only have 10 minutes left. So 1 second. So if we have, for example, let's say something like this, new data, and this would be an extreme outlier. So if we would use the fit method again, then we will kind of change what this 0 means. It won't be an outlier anymore. So it won't be that much of an outlier. I mean, here it's an extreme outlier, but here this information gets kind of lost because we fit it again. So what we want is really just transform it. So as you can see then, it's in relation to the others a much larger value. So it's always one point where we want to be careful that we don't use any test data to fit any parameters in our pipeline. Yeah, and if we want to use, I have to, I think, go back a little bit. Okay, so here I just fit and scored the pipeline. Here it's the accuracy score. It's just like the logistic regression, but with a standard scalar in front. And to access these steps, one question? Can you repeat this? Yeah, I didn't understand it completely. Yeah, so the question was, when I got it correctly, so what happens if the training data is not representative of the population and we do the standardization, and then the prediction would be kind of wrong because we got the wrong parameters? Yeah, that is the problem. I mean, I'm not sure how to deal with it. I mean, like the algorithms we use here, they assume or they work optimally only if our training set is a representative of the distribution of the population. Sorry. So one thing is, for example, this is also why we want to do the stratification, because if the proportions, if we have a very small data set and the proportions in training and tests are completely different, then yeah, it's not ideal. So we want to, it's a parameter estimation problem. So the larger your data set is, usually the law of large numbers, the more closely will your parameter estimation be to the real world population. But this is one assumption we have to make, that our training data set is really representative of what we want to predict. If it's completely different, then yeah, how can we learn from that, right? We could have sampled the data set maybe differently. We could have drawn smaller subsamples, but if we don't know the population parameters, I think there's no way to know how to resample our data set. Yeah, I'm sorry. I think it took a little bit longer than I thought. We only have like 5 minutes left, or a little bit more. Yeah. So maybe we can't talk. I mean, I will be here for the next 2 days. And if you want to talk about model evaluation, I'm probably not getting to this right now. Yeah. Dimensionality reduction. There are also 2 ways. You can select features or you can extract features. But yeah, you can maybe look at the Jupyter notebooks, and if you have questions, I'm happy to answer emails, really, because I'm sorry that I was a little bit slow here and didn't get to everything. And I already removed a lot of topics. 9 minutes is really tough. Yeah, this was one question that came up that I maybe want to, before I answer your question, I want to quickly get to. There was one point where someone said he changed the random seed, did the splitting, and got different performance estimates in his results. So in here I did exactly this exercise. So on the left, I split the training data of the iris set in 50-50. 50% of iris is training, and 50% of iris is test data. And in this case, I repeated this 50 times. And as you can see, the difference, there's a difference. Sometimes I get a 90% accuracy, sometimes a 100% accuracy. So usually the smaller the data set, the more pronounced this effect is. And also, the smaller your test set is, the more variance you have in your estimate. So for example, when I change it here to 90-10, so 90% is training data and 10% is test data, this variance becomes larger of the estimate. And the reason is, for example, it really depends then more on which exact sample end up in the test set and which sample ends up in the training set. And one way, a simple way, would be to just take the average of this. And there's cross-validation, k-fold cross-validation, and bootstrapping, maybe something you want to also look up later on after the session, which is very useful in practice. And for model selection especially. Yeah, I have a lot of points here, but really running out of time here. Yeah, so maybe look at this. I luckily put it in here. There's one document on the scikit-learn documentation where you can also read about model evaluation. But yeah, you can. I'm happy to answer questions, really. And if you want to, in general, look at further resources, maybe the scikit-learn website would be a good place. There are really extensive documentations about everything. And there's the mailing list. I think people will be happy if you join and ask questions. There are a lot of people helping people on the mailing list, answering questions. Also, in practice, I find Andreas Müller's cheat sheet very useful. So it's a cheat sheet that asks you a simple question. It kind of, as a beginner, guides you through what algorithm should I use on what kind of data set. Maybe something you want to check out. And yeah, Andreas Müller is also still writing his book, I think. I think he said last time it was finished in July when I was with him at SciPy, but I think it will be October 20th when I got it correctly now. And he will, I read the final draft and, or the draft, the latest draft, and it's a really great book. It's all about scikit-learn, so I think it will be the definite resource for scikit-learn. There are a lot of books about scikit-learn, but I think that is the most, I would say, accurate one. He's, Andreas Müller, also scikit-learn core developer. Will be out in 2 months.
For the theory parts, these are my two favorite books. The left one, Elements of Statistical Learning, it's a free book. I recommend this. This is also maybe my favorite one because it was my first machine learning pattern classification books years ago. So it has a special place in my heart. But they are both great. They talk about the statistical underpinnings of the algorithms. And yeah, if you're interested, I also have a small book here. Has also been, I think the Japanese one, or if you like German, and this is the original English one. But I didn't write these. Other people translated them, so I can't really vouch for them. I can't even understand or can't even read this, although the font looks pretty. Yeah, so if I have more resources on this GitHub repository with code examples, and like I said, I'm happy to answer questions later on. Again, then my email address, website, Twitter account, GitHub account, and the link to the material if you want to get the slides or something like that. And yeah, that's about it, I think. And yeah, I'm sorry that it's only 90 minutes. I could have talked about it for maybe 9 hours. I was at SciPy with Andreas last month, and we had, I think, 7 hours, and we didn't cover everything we wanted to cover. It was still not enough. So 90 minutes was a little bit challenging, but I hope you got some introduction at least to get into scikit-learn if you're interested, or maybe have some links to further resources where you can find more information. And yeah, ask me questions if you like. Yeah.